Hey everyone, so let's dive into a topic that is absolutely critical if you're serious about programming, asymptotic notations. Now, why should you care? Well, imagine you and a friend both write a program to do the exact same thing. How do you prove which one is actually faster? You can't just run them on your laptops and time them with a stopwatch, right? Your fancy new computer will always beat their older one. We need a fair, standardized way to compare them, and that's exactly what this is. It's the language we use to measure efficiency, and mastering it is key for writing great code and, let's be honest, for passing those tough technical interviews.
So think of it like this. We're looking for a universal language for performance, something that lets us talk about how an algorithm behaves not in seconds or milliseconds, but in terms of how its hunger for resources like time or memory grows as the amount of data we feed it gets bigger and bigger. It's all about understanding the rate of growth, the fundamental character of the algorithm, completely separate from the hardware it's running on.
So here's our game plan for today. We'll start by looking at our three main tools for analysis. I like to call them performance lenses. Then we'll take them for a spin on a nice simple example. After that, we'll throw them a curveball with a much harder problem. We'll talk about what makes an answer good versus just correct, and we'll wrap it all up with the key rules you need to know.
All right, let's get into our toolkit. To really understand an algorithm, we can't just look at it one way. We need to see it from a few different angles. These are our three lenses. The famous Big O, its counterpart Big Omega, and the one we're always hoping for, Big Theta.
First up, the one you've probably heard of, Big O. This is our pessimistic lens. It tells us the upper bound on how long something will take. Think of it as the worst-case scenario. It's a guarantee that your algorithm will never be slower than this, no matter how unlucky you get. It puts a ceiling on the performance. So if Big O is the pessimist, what's the optimist in the room? Well, that would be Big Omega. It's the total opposite. It gives us the lower bound, the best-case scenario. This sets a performance floor. It guarantees that the algorithm will take at least this long to run. It's never going to be faster than its omega bound.
And finally, we have the one we really want, the just right of the three, Big Theta. This is our precise lens. A theta bound is a tight bound, and it only happens when the upper bound from Big O and the lower bound from Big Omega are basically the same. It's like we've perfectly sandwiched the performance, telling us exactly how this algorithm scales.
Okay, quick recap. Big O is the ceiling, the upper bound. It answers, how slow can this possibly get? Big Omega is the floor, the lower bound. It asks, how fast can it possibly be? And Big Theta is that perfect fit, the tight bound that tells us, yep, this is pretty much exactly how fast it is. Got it? Good.
All right, enough theory. Let's get our hands dirty and see how this actually works. We're going to start with a really straightforward example, a simple polynomial, just to get a feel for how these three lenses work together.
So here's the function we're going to analyze. 2n squared plus 3n plus 4. Now, the first and most important rule of asymptotic analysis is that you focus on the term that grows the fastest. As n gets huge, that n squared term is the heavyweight champion. The other parts, the 3n and the 4, become like little ants next to an elephant. They just don't matter in the long run. So let's prove it.
First, let's find that Big O, our performance ceiling. We know n squared is the dominant term, so we're looking for a way to say our whole function is less than or equal to some multiple of n squared. Well, let's think about it. 2n squared is definitely less than or equal to 2n squared. And for any n bigger than 1, 3n is smaller than 3n squared, right? And 4 is definitely smaller than 4n squared. So if we add those up, our whole function has to be smaller than 2n squared plus 3n squared plus 4n squared, which is just 9n squared. And there you have it. We found our ceiling. The function is O of n squared.
Awesome. Now let's find the floor using Big Omega. This is actually even easier. Look at our function again, 2n squared plus 3n plus 4. Since 3n and 4 are always positive numbers, we know for a fact that the whole expression has to be bigger than just 2n squared by itself. And 2n squared is obviously bigger than 1n squared. So we've just proven that our function is always greater than or equal to 1n squared. That's our floor. We can say the function is omega of n squared.
And now for the magic moment. Check this out. Our upper bound, our ceiling, is in the family of n squared. And our lower bound, our floor, is also in the family of n squared. They match. We've successfully sandwiched our function. And when that happens, we get to make the most powerful statement of all. Our function is theta of n squared. That is the perfect fit, the most precise description we can give.
Okay, that last example was pretty neat and tidy, but the real world isn't always so cooperative. What happens when you can't find that perfect sandwich? What do you do when the upper and lower bounds just don't want to meet? Let's tackle a much tougher function to see why big O and omega are still so important.
Okay, our next opponent is the factorial function. Remember this one? N factorial is just n times n minus 1 times n minus 2, all the way down to 1. And this function grows, it grows ridiculously fast. It makes finding a nice, simple, tight bound a real challenge.
So, how in the world do we put a ceiling on this thing? Let's try a little trick. We know n factorial is a product of n different numbers. The biggest one in that list is n itself. So what if we made an easier, bigger version by replacing every single term in the product with n? Then we'd have n times n times n, n times. And what is that? It's n to the power of n. So we found a valid upper bound. nn is O of nn. It's a correct statement, but wow, that is a huge bound.
Now for the lower bound. We can play the same game, but with the smallest number. Every term in that multiplication is at least 1, right? So if we replace them all with 1, we get 1 times 1 times 1, which is just 1. This gives us a technically correct lower bound of O of 1. But, come on, saying something grows at least as fast as a constant is not exactly helpful, is it?
And here's the problem. Our ceiling is this astronomical nn, and our floor is 1. That's not a sandwich. That's the distance between the Earth and the Sun. The gap is enormous. And this shows us a really critical lesson. For some complicated functions, you just can't find a simple, tight theta bound. And in those situations, the best you can do is find the tightest possible big O and the tightest possible big omega you can, even if they're worlds apart. This whole factorial mess brings up a really important question, something you absolutely have to understand. What makes for a good answer in algorithm analysis? Because as we just saw, just being technically correct isn't always enough. There's a huge difference between correct and useful.
Let me give you a real-world analogy to make this crystal clear. Imagine you walk into a store to buy a new phone, and you ask the salesperson, hey, what's a good price for this? The kind of answer you get back is a lot like the bounds we've been talking about.
So if they tell you, oh, it'll cost you at least $3,000, well, no kidding. That's a lower bound, an omega. It's true, but it doesn't help you budget at all. What if they say, well, it'll be at most $100,000? Again, probably true, but completely useless. That's a loose big O. But if they say it's going to be around $20,000, now we're talking. That is a tight bound, a theta. It's correct and it's useful. It's information you can actually do something with. And that is the absolute bottom line here. Our goal is never just to find an answer that's technically correct. Our goal is to find an answer that is useful. And in the world of algorithm analysis, useful means tight. The tightest possible bound you can find is always the best answer.
Okay, let's bring it all home. We're going to summarize everything into a few key rules that you need to burn into your brain. This is the step that's going to come up on your exams and in your technical interviews, so pay close attention. Here's your checklist. Number 1, theta is king. Always try to find a theta bound first. It is the gold standard, the most precise answer you can give. Number 2, sometimes you just can't find it, and that's okay. That's what big O and big omega are for. They let you describe the ceiling and the floor even if they don't meet. Number 3, and this is super important for getting full marks, when you give a big O or an omega answer, you must make it as tight as possible. Saying an algorithm is O of n squared when it's really O of n is technically true, but it's a terrible answer. And finally, number 4, always remember the phone analogy. A correct answer isn't worth much if it isn't useful. Precision is what matters.
So I'll leave you with one last thing to chew on. We've just spent all this time establishing that theta is the perfect, most precise answer we can give. So why is it that if you go out into the real world, in interviews, in articles, online, everyone just talks about big O? Why is that the one that gets all the attention? Think about what big O really represents, that worst-case scenario, and why that might be the thing we care about most when we're building reliable software. Thanks for watching.